What really is integration? Despite what you might have been told, integration isn't an antiderivative. The integral as an antiderivative is generally only useful in the context of symbolic integral algorithms such as the Hermite-Strugatsky algorithm. To understand integration, we have to understand sets and their measures. The size or cardinality of a set, denoted by the Hebrew letter Aleph, describes the length of a set. Size has nothing to do with the value of objects in the set, but instead its lateral size. For example, the set of even numbers and integers is the same, because for every value of n, there is a corresponding value within both sets, such that their domain's measure is equal. These two sets are both counted at infinity, but the set size of inverse n is larger than the set of the inverse square. This is because the domain of inverse n can always logarithmically partition into groups of 1, but the set of the inverse square, by the properties of the exponentiation of the logarithmic sum, which when exponentially decayed produce the analytic continuation of the Riemann zeta function, converges, and thereby its domain cannot map values to groups of 1. So it is smaller than the inverse of n, despite both being counted at infinity. The next important concept of infinity is the continuity of an interval. Here, we have the interval of 0 to 1 as the union of all set partitions 0 to 1 over n, to which the minimum is the limit as n approaches infinity, and the maximum is n at 1. Therefore, the length of the set is 1. Now we can start understanding integration. First, let's say you wanted to integrate a function across the interval 0 to 1, and you don't have a Riemann integral. We could instead use the prior knowledge of set measurements to try to construct our own integral. First, we can take the preimage of the set, which redefines the lateral interval, and bounds the height to a max and min of 1 and 0. Then we can take the union of sets from the smallest value of the preimage to the largest value on each bound, with respect to the length of the measured set. This gives us our integral, also called the Lebesgue integral.